This is our momentum fourth video lesson, and I accidentally called the third one fourth, but this is the fourth one. The previous one was the third one. Let's start with this question, number 68 on our lesson. A large cannon is mounted to a cart with frictionless wheels that is initially at rest on a horizontal surface. The cannon fires a large cannonball to the right with a speed v cannonball, which is then caught by a trap firmly attached to the cart. What is the final speed v of the cannon cart cannonball system? This is a tricky question. You have to think about what is the momentum of the system before. The momentum of the system before is 0. So you have the mass of the cannon, you have the mass of the cannon, you have the mass of the cannonball, and you have the mass of the block. All of them are not moving. Their initial velocity is 0. And then afterwards, you have the mass of the cannon, velocity of the cannon, plus the mass of the cannonball, velocity of the cannonball, and plus the mass of the block, velocity of the block. But because the cannonball is caught by the block, I can combine these guys together, and I will say that their momentum, so the mass of the block and the mass of the cannonball together, and their velocity, let's call it block velocity. And because they say the large cannon is mounted on the cart with frictionless wheels, the wheels are frictionless, but the cannon is mounted to the cart. So I also could say that, yes, it is very tricky. I also could say that all of them together afterwards, so the mass of the cannon, the block, and the cannonball together, because the cannon is mounted and the block is mounted. The only part that was moving is the cannonball. And because my momentum before is equal to momentum after has to be equal to 0. And the only value there it has to be equal to 0 is the velocity of the ball. Or velocity of both of them, right? After, we don't have to say this. It's going to be the velocity of both of them, or the one that they ask me, that the final velocity. I'm going to call this the final velocity of the system. So the final velocity of the system must be equal to 0 meters per second as well. Here's the next question I want to look with you at. We have it online in our lesson. A tennis ball of mass m rebounds from a vertical wall with the same speed v as it had initially. What is the change in the momentum of the ball? So let's look at the momentum of the ball before it. The ball has horizontal momentum and vertical momentum. And its resultant momentum is this direction. So the horizontal momentum, so this is angle theta as well. The horizontal momentum is mv cosine theta, and the vertical momentum is mv sine theta. And the same happens after. The momentum of the ball afterwards is this way, mv, the same mv, but it also has horizontal component, mv cosine theta, and it has vertical component, mv sine theta, because this is our angle, correct? So the green one is mv sine theta. So I'm going to look at the change of the momentum horizontally and vertically. The change of the momentum horizontally, I have the final, which is to the left. So that is going to be, I'm going to choose, doesn't matter. So I have negative mv cosine theta minus initial. Initial was in the positive direction, so that's mv cosine theta. So the change of the momentum horizontally, I have negative mv cosine theta, but because they don't include anywhere angles, I'm just going to take the magnitude of it. It gives me negative 2 mv cosine theta. So that gives me 2 mv cosine theta. So that is horizontal. The change of the momentum vertically is, at first it's moving up and then continues moving up. So I have the final, which is mv sine theta, minus initial, which is mv sine theta. So the vertical momentum is 0. So the total change of the momentum in the system is equal to 2 mv cosine theta. Another tricky question. Here's another question I want to look with you at. A cannon is rigidly attached to a carriage which can move along horizontal rails but is connected to a post by a large spring, initially unstretched and with a force constant of 1.9 10 to the 4th newtons per meter as shown. The cannon fires a 200 kilogram projectile at a velocity of 125 meters per second directed 45 degrees above the horizontal. If the mass of the cannon and its carriage is 500 kilogram, find the maximum extension of the spring. So my thought is going to be the same. I have to look at the horizontal component of the velocity and the vertical component of the velocity after it was fired. And for vertical momentum before, momentum after, I cannot look at it because vertically the cannon is not going to be moving vertically. The energy of the cannon after the collision or after the firing of the ball is going to go into the ground. So I'm not going to look at the vertical part of the velocity here, but I need the horizontal part of the velocity of the cannon ball. So if this is the velocity of the ball after it was fired, and the cannon is going to be moving horizontally with some velocity v cannon, then I can use conservation of momentum before and after. So for conservation of momentum, I'm going to have the momentum of both of them before is 0 because neither cannon or cannonball are moving. And the momentum after, I have the mass of the cannon, velocity of the cannon, plus the mass of the ball, velocity of the ball, but I'm looking at the horizontal part, and the horizontal part is v cosine theta, v of the ball cosine theta. So I have v of the ball cosine theta. Now if I plug in my numbers, I can calculate my velocity of the cannon. So the velocity of the cannon is equal to, I'm going to plug in the numbers and solve it. So I got the velocity of the cannon is 3.5 meters per second. And it's negative 3.5 meters per second. So I have equals to negative 3.5 meters per second. So it moves in the opposite direction of the cannonball. Now, since I know the velocity of the cannon right after collision, the cannon has kinetic energy. So the kinetic energy of the cannon is 1/2 its mass and its velocity squared, 3.5 squared. I don't need negative number because plug in negative number because when I square it's still gonna be positive. So I got energy of the cannonball is 30,625 joules. So this is how much energy the cannon has right after it fires the cannonball. But then eventually cannon stops and it will stretch the spring. So all this energy is going to go into the potential energy of the spring because after the cannon stops, all the energy is now stored in the spring. So I'm going to say that the energy of the spring, which is 1/2 kx squared, is equal to 30,625 joules. So if I plug in my numbers, so I have 1/2, K is given 19,000, and x squared equals to 30,625. So x is equal to 1.8 meters. So here's one more question that we're gonna look in this video at. A pendulum of length 1 meter and bob has a mass of 1 kilogram is released from rest at an angle of 30 degrees from the vertical. When the pendulum reaches the vertical position, the bob strikes a mass m 3 kilogram that is rested on a frictionless table that has the height of 0.85 meters. When the pendulum reaches the vertical position, calculate the speed of the bob just before it strikes the box. I'm going to cover the rest of B, C, D, E just to have space to do calculations. So I redrew the picture so I will have a little bit more space to do my calculations. And I'm going to look at this information. So the ball is raised from its equilibrium. So let's say right here would be the equilibrium. So when it reaches the bottom, it doesn't matter where the bottom is, but if it is right here, then it is at certain height. It is at certain height. So if this length is L, then if I look at this triangle, this is L sine theta, and this part of the triangle is L cosine theta. So the height that the ball is raised at is equal to L minus L cosine theta. So when the ball is raised to this height, or pendulum, then it has potential energy. So the potential energy of the ball is mg, and the height is, I'm gonna factor out, or let's do it first, L minus L cosine theta. And that will be transferred to the kinetic energy right before it hits the green box. So that will be 1/2 the mass and the velocity of the ball right before it hits the mass, the green m mass. So now I can cancel mass of the ball and factor out L from the from the left side. So I have Lg, and then I have 1 minus cosine theta, and that is equal to, I'm going to times both sides by 2 and get rid of the fraction, and I have VB and square both sides. So that is the velocity of the ball. So if I plug in my numbers, I will find reaches the vertical position. Calculate the speed of the bob just before it strikes the box. That's going to be the speed of the bob right before it strikes the box, and that is 1.62 meters per second. So if you plug in the numbers for L is given, angle is 30 degrees, and this one is not needed yet. And the height is this height, so it's not, maybe we should not call this as a height. Let's call this a slightly different height, like big H. So let's call this, so this is your big H, mgh, the potential energy. And that is it, that's all is given. Oh, and the mass of the little ball, but we don't need it. So L is given, L is 1 meter, G is 10, and cosine is 30 degrees. So if I plug in my numbers, I get the velocity of the ball right before it strikes the green box, 1.62 meters per second. So for the next part, they ask you to calculate the speed of the bob in the box just after they collide elastically. So I can use conservation of momentum. So if I use conservation of momentum, I'm going to say the mass of the ball and the velocity of the ball, the one that we just found 162 before, plus the mass of the block times its velocity before, equals to the mass of the ball, velocity of the ball final, plus the mass of the block times the velocity of the block. Let's call it B final. Let's just call it the V, and then final, or just let's call it V. So the velocity of the block after the collision is going to be some velocity V. And from here I can see that maybe let's call this one final, so we don't have too many letters written. So final. So that's going to be the velocity of the ball final, and the velocity of the block is going to be V. I don't have enough information to solve this because they don't give me the velocity of the ball right after the collision, and they don't give me the velocity of the block right after the collision. So, but they say it's elastic collision. Because it's elastic collision, energy is conserved. So I can say the energy of the ball is 1/2 the mass of the ball, velocity of the ball squared. Energy of the block is 0 because it's not moving, and equals to 1/2 the energy of the ball and after, and energy of the block after. So I have this system of two equations with two unknowns. I do not know the final velocity of the ball, and I do not know the velocity of the block. So I'm gonna solve for the, let's see what they ask me to find. They ask me to find the speed of the bob and the box. It doesn't matter, I need to find both of them. So let's solve for V final, the top equation. So we have the V final, the velocity of the ball right after the collision is equal to mass of the block, velocity of the block, minus the mass of the block, mass of the ball, velocity of the ball, minus the mass of the block, velocity of the block after, and divide by the mass of the ball. Now, since I know this part, since I know the velocity of the final velocity of the ball right after, I can plug it into my equation, and this is what I'm gonna get. Let's times them all. Oh, actually we can cancel all of them by 1/2. 1/2 can be cancelled, or times all of them by 2. So what I have after, if I plug into my kinetic energy formulas, I have mass of the ball, velocity of the ball squared is equal to mass of the block, mass of the ball, velocity of the ball final. So I have to square the whole thing. So this whole thing has to be squared, because it's squared over there. So I have mass of the ball, velocity of the ball, minus mass of the block, velocity of the block, over mass of the ball, and plus the mass of the block, velocity of the block squared. I'm going to simplify them all, and I see that I have mass of the ball here, and I have the mass of the ball right here, but it also squared. So I can cancel one of them from the top and the bottom, and I'm going to have only one of them at the bottom. And the top one, I'm going to use the equation. So I'm going to use this one, A minus B squared is equal to A squared minus 2AB plus B squared. So I have mass of the block, velocity of the mass of the ball, velocity of the ball, both of them squared, minus 2 times their product. So I have 2 mass of the ball, velocity of the ball, mass of the block, velocity of the block, and the last one squared will give me plus the mass of the block, velocity of the block squared, and I still have my mass of the block, velocity of the block. Now I'm going to times them all by mvb. I'm going to times them all by mb. So this term, and this term times by mb to cancel mb from my fractions, and I will get, so after I times them all by mass of the ball, I have m squared on the left side and no fraction for the first term where I underlined yellow, and then I have the last term. So I have the first term, I have the second term now without the fraction, and the last term I had to multiply by m of the ball. Now the mass of the ball is 1 kilogram, or actually I have this term on both sides, so I can cancel these from both sides. And what I'm going to be left with, and because I only have, let me rewrite this. I'm going to move 2m b v b m v to the left side, and what's left on the right side is v squared. So I will have m squared v squared plus mv squared and mass of the ball. And because every single term in this case, this term, and this term, all of them have velocity, I can cancel that velocity, so I don't have that value. And now I'm gonna plug in the numbers. So the mass of the ball is 1 kilogram, so I have 2 times 1. Velocity of the ball we just found is 162. And the mass of the block is 3 kilogram. Now the mass of the block is 3 kilogram squared. I'm looking for V, plus the mass of the block, velocity of the block that we are looking for, and the mass of the ball is 1. So if I collect my like terms and solve for the velocity of the block, I will get 0.81 meters per second. Now I can take this value and plug it into my final velocity, V final velocity of the ball. So if I plug this in, I will get this equals to negative 0.81 meter per second. So the ball strikes the block, and after the collision, both of them have the same velocity, 0.81 meter per second, but in opposite directions. So my answer for this part is that they both have the same velocity of negative 0.81 for the ball and 0.81 for the block. For C part, they ask you to determine the impulse on the box during the collision, and the impulse is equal to the mass of the block and change of its velocity. So the mass of the block is 3 kilogram and its final velocity is 0.81 and its initial velocity is 0. So that will give me the number of 243 kilogram meters per second, or newtons times seconds. So that is the answer for C. So that's 2.43 newtons times seconds. So that is for the impulse. For the next question, they ask you how far the block is going to strike the ground. So you have to find the value of delta x. And because I know the velocity of the block right after the collision is 0.81, and when it hits the ground, it will have some final vertical velocity. And I can calculate the vertical velocity by knowing the height and acceleration due to gravity, because there is acceleration and there is the height given. So the distance and the height, the distance and the acceleration given, I can use the DA formula to find this final velocity. So that final velocity is going to be equal to the square root of 2 acceleration due to gravity, the height where the box was, plus its vertical initial velocity, but that one is 0. It has horizontal velocity but not vertical as it leaves the table. So I have the square root of 2 times 10 and times the height. They tell me the height is 0.85. So that height, this height at where the box is located is 0.85 above the ground, and that will give me the answer of 4.12 meters per second. So the vertical velocity when it strikes the ground is 4.12 meters per second, and because I know the final velocity, I can use the acceleration formula, which is the change of the velocity over time. So if I want to solve for the time, it's the change of the velocity over the acceleration. So for the vertical change of the velocity, vertical velocity, initial is 0 and final is 412. So that is 4.12, and the acceleration is 10. So I get 0.412 seconds. That's how long it will take for the box to land on the ground. Now, since I know the time and I know horizontal velocity is 0.81, I can find delta x, or the distance it travels. That is the average velocity horizontal times the time it moves horizontally. So the horizontal velocity is 0.81. It's 0.81, and times is 0.412. So that will give me the answer of 0.34 meters, or 34 centimeters. That's how far the box is going to land on the ground from the table. Now they make it a little bit more complicated. They say at the location where the box would have struck the floor, now a small cart of mass, and also mass is 3 kilogram, and negligible height is placed. The box lands in the cart and sticks to the cart in perfectly inelastic collision. Calculate the horizontal velocity of the cart just after the box lands in it. So I have to use conservation of momentum. I'm gonna say, so this one is m, and the second one is also m. So I have the momentum before, I have the block is moving with the velocity of 0.81, and the cart is not moving but has the same mass. And afterwards they stuck together, so that's two of their masses, and I'm looking for their velocity. So perfectly inelastic collision when one stuck with the other. So every single one of them has a mass, so I can cancel that. And I find the velocity of both of them afterwards is 0.405 meters per second. That will conclude our last and the final video in momentum, video 4. Unless you email me and ask me to do more questions related to the momentum, you will see in this description whether there is video 5 or not. But for now, that's going to be it, and that's it. See you in the next video.